So hi, I'm Grebla. I'm a postdoc in Columbia University in the electrical engineering department. And what I'll describe to you here today is my work on coordinated multiple joint transmission in cellular networks. So what we consider a cellular network that has this technology called coordinated multipoint with joint transmission, where more than a single base station can joint transmit to a user to increase the probability of success of transmission of a packet. The benefit is mostly to users who are between two cells of the network because they suffer from more interference because they have roughly the same distance from two base stations. There have been related work in the field. It is closely related with the concept of network MIMO. So there is many informational theory work that discuss the benefit from doing the joint transmission. There's also some heuristic talk about how to schedule packets. What we try to do here is we essentially develop algorithms with performance guarantee while we stick to the building blocks of the standard. So we first discuss the model of how two base stations can jointly transmit to a user. And if you want to do the joint transmission, you need to transmit on two scheduling blocks in the subframe. So you have 1 millisecond subframe, which is the column here. And the two base stations need to transmit and using the exact same block to the user so that the user just experience high SNR without actually doing anything special. In terms of its antenna, it just sees a better signal. So the kind of difficulty here is to align these blocks in frequency. And this results with a higher success probability. So when we model our problem, we consider that we have some pending packets to transmission within this subframe, and each packet is associated with a size, which is the number of blocks it will take to transmit this packet. And there's also a utility associated with each packet, which is how much utility you get from a successful reception of this packet. What we have is we have some constraint on each subframe, which is the number of scheduled blocks, which is determined by the bandwidth of the system. And we need to pack the packets into these subframes and determine which one will use joint transmission such that we maximize the total expected utility. We show that the problem is NP-hard even for specific cases where the utility is 1, but obviously for the general case. And we solve the problem by decomposing it into two components, which is knapsack and coloring. The knapsack is from packing the packets, but the difficulty again is this alignment of joint transmission, so this is what makes the coloring aspect. So we first solve the knapsack problem, then solve the coloring, but again, it's not just solving the knapsack, we need to solve it in a way that will guarantee that we would be able to color the resulting graph. And coloring it will assure that we can align the schedule blocks. So we developed two algorithms. One is based on matching and one is based on star topology. The one based on matching, we are able to solve small instances of the problem considering two base stations that can joint transmit. The weight is associated with an edge between these two base stations. So each base station is a node and the edge is if base stations can cooperate. And when we select a matching, this will yield us the solution, and it gives a performance guarantee of this, which is 2 times alpha over 3 times the number of blocks, where alpha is the approximation ratio used to solve the packing problem. We also develop another algorithm, which is based on star topology. This time we assign a weight to each node, which is each base station. We essentially solve the problem for this node, this base station, and its neighbors, and the resulting utility is the weight of this node. And then we show that by iteratively choosing the one that has maximum weight, we actually get this approximation ratio, which is alpha times S. Again, alpha is the approximation ratio of solving the knapsack problem. We then extend this problem to consider a queuing system that evolves over time. So before we were scheduling in one subframe, 1 millisecond, but now we consider several subframes and a queuing system. And we show that if we schedule in each subframe the problem by considering a specific utility function, which is the size of the queue times the success probability for single transmission, and the difference between the queue size of joint transmission and the queue size of single transmission times the success probability for the joint transmission, then we show that if you solve in each subframe the problem optimally, you actually get a throughput optimal scheduling policy. So we prove that. And to conclude, we do an evaluation study. So we try to evaluate how much benefit we'll get from the different algorithm. We also study the backhaul capacity and how it affects the performance, because you need bandwidth, of course, to transfer the packet from one base station to the base station that will transmit jointly with it. And what we show is that when we increase the backhaul capacity, So both algorithms increase in throughput as expected. You can see the diminishing return. And we see that our matching-based algorithm performs worse than the other algorithm because obviously its approximation ratio, as we claimed before, is worse. However, it also catches up eventually as we increase the backhaul capacity.